All right, so today we're going to talk about basic probability, and I really mean very basic probability, just like the chances of landing on heads when you flip a coin, or rolling a die and getting a 6, or any of those, basic events before we start getting into some of the harder probability topics. So the chances of an event A occurring, okay, so that's the probability of A. It's going to be the number of ways that A can occur, so basically how many times is A existing in your sample space, divided by the total number of events in your sample space. So for example, if you're talking about, a coin landing on heads, there's only two options, heads or tails. That's the number of events in your sample space. There's only one way it can land on heads, so 1 out of 2, and that's why the probability of landing on heads would be 1/2. If you're rolling a die, what is the chance of getting an even number? So the chances of getting an even number. Well, how many even numbers are there on the die? When you roll a die, there's 6 sides. So 1, 2, 3, 4, 5, 6. So that's 2, 4, and 6. That's 3 even numbers out of 6 total options that you can get when you roll that die. So the chances of getting an even number is 1/2. The chances of getting an odd number actually also happen to be 1/2. You'll notice that when you add all the events of a sample space together, they add up to one whole. Something has to occur, okay? Probabilities always fall on this spectrum right here, okay? When something has a probability of 1, this means that it is definite, it is absolutely going to occur. For example, what are the chances, I'm trying to think of something right now. What are the chances that the clock is moving right now? Okay, yes, the time is moving. Time does not stop. So therefore, it is definite. The probability is 1. Okay, so then what about if you have a probability of 0? This is something that's impossible to happen. Okay, so what are the chances that it is July 45th? It is not July 45th. There is no July 45th, so the probability of that happening is 0. The closer you are to a probability of 1, the more likely it is to occur. The closer it is to a probability of 0, the less likely it is to occur. If you roll the same die 10 times, on the 10th time you roll, what is the chance of getting an even number? As I roll that die, unless I'm changing something like weighting the sides or anything like that, it doesn't matter if I rolled that die 57 times, 157 times, 157 billion times. Every time you roll that die, it's the same chance of something happening, okay? So the chance of getting an even number is still going to be 3 sides out of 6, which comes out to be 1/2. Okay, so keep that in mind if you ever, let's say, for example, play lottery. People are always saying, oh, it didn't come up on, this number or this number this time. It's bound to come up on my number. Sorry to break it to you, but it's not. The chances of a number coming up is the same every single time that you play that lottery. The only difference is how many people play the lottery depends on how many people actually are going to win money. Okay, so just keep that in mind. So then we get into probability with this spinner in the next one. So consider the spinner to the right and determine each probability. So if I had a spinner, so let me add a little thing here. Imagine this is going to be flipping around. What are the chances that I land on an even number? Let's take a look. I have 6 sides in total, or 6 places in total. An even number would be 2, 4, or 6. So 2, 4, or 6 would be 3 out of 6. The chances of landing on even are 1/2. What are the chances of not landing on a 2? Well, here's my 2. How many sides do I have left that are not 2? 1, 2, 3, 4, 5. So it would be 5 out of 6. Okay? What's the probability of landing on a prime number? Prime number is a number that is only divisible by itself and 1. 1 is included in that. So 1, 2, 3. 4 is divisible by 2, so that does not count. 5, and then 6 is divisible by 3 and 2, so that doesn't count. So that's 4 out of those 6 numbers, which comes out to be a probability of 2/3. What's the probability of getting a blue? Okay, so that's 3 out of those 6, which is 1/2, and I'm going to add in 2 extra things. What is the chances of getting blue and even? And what is the chances of getting blue and 3? Okay, so blue and even. So let's take a look. How many of these are blue and even? So 2 is blue, 2 is even. It's the only one that is blue and even. It's a 1 out of 6. What about blue and 3? Okay, well, unfortunately, 3 is not blue. There's no possible way of getting blue and 3 at the same time because, again, you're only spinning once. This pointer is only landing on one little section. So the answer for that would be 0. That is impossible. Okay. And then let's say I wanted the probability of landing on, a number from 1 to 6. Well, that's definite, so that would be a probability of 1. All right, so conditional probability. It's a pretty big section of probability, I would say. If things come up in probability on the Regents and the final, I feel like it's more likely to be conditional probability than just basic probability. Conditional probability has to do with focusing on a specific grouping within your larger population. So I have an example of what we call a two-way table. I can read down here what salaries people have. I can read across what education levels people have. What might be helpful for me is to actually find out the totals here along all of these edges. So I'm going to do that before we start calculating anything, because that's going to tell me how many people are involved, how many people are in each category. Okay. And it's going to just make my life a lot easier when I start getting into actually doing calculations. I should mention, as I'm doing these calculations here, be really careful when you do stuff in your calculator. Your calculator is only as good as the information you put into it. If you make mistakes when you're typing stuff in, you're going to obviously have inaccurate values that the calculator is going to give you, and you're not going to have any work to show for it. So just be careful. That's a good general rule of thumb in all cases when you are working with the calculator. Okay, almost done. 178 plus 245 would be 436, and then I'm going to add these together. 296 plus 505 plus 404 comes out to be 1205. And just to double check, when I add down this way, it should come out to be the same. 107 plus 224 plus 438 plus 436 also comes out to 1205. Okay. So if I'm going to do a probability out of everyone, it's going to be out of the 1205 employees that I have in this situation. So for example, what are the chances that if I pick a randomly selected person, that this person has less than a high school education? So less than a high school education, the total number of people that have less than a high school education is 107 out of the 1205 people in the entire population. So if I want to just get an idea of how likely that is, 107 divided by 1205, it's 0.08, so that's about 8%, pretty unlikely. Okay, so most people have more than a high school education. It's fine, by the way, if you leave your probabilities as fractions. You don't have to make them decimals. Okay, what are the chances that if I pick a randomly selected person, they earn over $30,000 and they have less than a high school education? Okay, so I'm going to try to match up like where this meets in my table. So earns over $30,000, so that's everybody in this column right here, but they also have to have less than a high school education, so that is right here, only 2 out of those 1,205 people in my total population. 2 out of 1,205, it's 0.001. That's less than 0.1%. So obviously that is extremely unlikely to occur. When you start seeing this little bar here, this is when you start seeing what we call a conditional probability. Okay, that bar, what comes after that, that's what we are given. That's the specific group of people we're going to focus on. Instead of out of all of our people, 1205, you're going to focus only on that second group and find out what are the chances of this happening in that second group. So what are the chances that someone earns over $30,000 given that they have only a high school education? Okay, so high school education. So given that they have a high school education, I'm going to focus on the 224 people who have a high school education. So my denominator is 224 now. Instead of everyone, it's just the 224. What are the chances that this person earns over $30,000 given that they only had a high school education? Well, how many of these 224 earn over $30,000? It's only 14. So 14 out of 224, and again, how likely is that? Obviously, you can tell it's pretty unlikely, about 6%. What are the chances that someone has a high school education given that they earn $20,000 or more? So this is a little tricky. Given that they earn $20,000 or more. So let's find out how many people earn $20,000. Okay, $20,000 to $30,000 is 505. Or more, that's actually both of these, 505 plus 404, which would be 909. So you're going to focus on these two rows right here. So now how many of those people have only a high school education? That would be 98 plus 14. Okay, so we're focusing on these two rows, 98 and 14 of the people only with high school education. 98 plus 14 is 112. Okay, so 112 out of 909 is the chance that someone earns 20,000 or more given they only have a high school education. And then finally, what are the chances someone earns over 30,000 given that they have a college degree? So given college degree means you're going to focus just on the people who have a college degree, those 436 people. Of those people, how many earn over 30,000? 245. So you can see 245 over 436. That's over 56%, so you can see there's a much larger likelihood of earning more money when someone had a college degree in this specific grouping we're looking at. Okay, sometimes if you're not given a two-way table, you'll have to set up a two-way table and then answer the certain questions in that problem. So a room is selected randomly at a downtown hotel. The probability the room has a king-sized bed is 62%, and the probability the room has a view of the town square is 43%. If the chance that a room has a king-size bed and a view of the square is 38%, complete the two-way table below and answer each question. Okay, so to make a two-way table, you're going to set it up so it's 4 by 4. You want the totals along the bottom and the totals along the right always to add up to be the same thing. When you're dealing with percentages, the best thing you can do is have your total to be out of 100. We're going to say it's like a hypothetical 100 rooms in this hotel. Even though we don't know exactly how many there are, we're going to say hypothetically so that way it kind of like feels like it makes a little more sense in our head. What are the two classifications we're looking at? King-size bed and view of the town square. So king-size bed and not having a king-size bed, view of the town square and not having a view of the town square. So this not and this not are really the same thing. This is just more of a symbol that represents that. So the chances of having a king-size bed out of these 100 rooms, 62% would mean 62 of those hypothetical 100 rooms have a king-size bed. So now the total has to add up to 100. So do 100 minus 62, and you'll find out that 38 do not have a king-size bed. It says that there's a 43% chance of having a view of the town square. So the view is 43. So hypothetically, out of those 100 rooms, 43 have a view. 100 minus 43 means 57 do not have a view. And then finally, the chance that a room has both a king-size bed and a view of the square. So where the K and the V match up, 38 of these hypothetical 100 rooms have both a king-size bed and a view of the town square. So now you just have to add or subtract and fill in all the rest of the boxes, and you should be able to answer almost everything else that's left. So 43 minus 38 means that I have 5 here. 5 plus 33 is 38, and 57 minus 33 is 24. And just to check, 38 plus 24 is 62. So again, all your columns and rows should always add up to the totals that you have on each side. So let's try the first probability. What are the chances that the room doesn't have a view and doesn't have a king-size bed? Okay, so no king-size bed, no view. That's 33 out of 100, which again, you could make 0.33, 33%, or just even leave it as 33 out of 100. That's fine. What are the chances that it has a view or a king-size bed? So you need to add up all the rooms that have a view, have a king-size bed, or have both, but don't add up the overlap more than once, okay? So I have rooms that have no view but have a king-size bed is 24, okay? Rooms that have both a king-size bed and a view is 38, and rooms that just have a view but don't have a king-size bed is 5 out of our total 100 rooms. So 24 plus 38 plus 5, that's 67 out of 100 rooms, okay, or 0.67, or 67% of rooms will either have a view or a king-size bed. So now we start getting into these given probabilities, okay, these conditional probabilities. You're going to focus on this specific row or column and see what are the chances of this happening out of this specific grouping, not out of everyone. So given that there is a king-size bed, so you focus only on the 62 rooms that have a king-size bed, so it's out of 62. What are the chances that a room has a view? The room that have a view is 38. So 38 out of 62 comes out to be 61%. So pretty likely that if you have a king-size bed, you're going to have a view. Okay, what are the chances that you have a king-size bed given that you have no view? Okay, so given no view, given no view would be 57 rooms. So of those 57 rooms, okay, of no view, what are the chances that there's a king-size bed? King-size bed is 24. 24 out of 57 is 42%. So it's likely, but again, being that it's less than 50%, a little less likely. The most important thing, again, you focus on the specific row or column from the given and you see how many fit this quality out of this many. Okay, so you'll notice in that last set of problems when we were working on conditional property, we were talking about connections between like having a view of the town square and a king-size bed, and you might be wondering, does having a view of the town square affect having a king-size bed and vice versa? And what you're checking there is you're checking the independence of events, of the probabilities of events. Do the probabilities of these events affect each other? If they don't affect each other, then you say they are called independent. But if they do affect each other, then they're not independent. They're dependent. They affect each other. So let's look at the example that we had talked about before in the previous example with the rooms with the view and the king-size bed. Okay, remember, to fill in this two-way table, what you're going to do is you're going to take, and again, imagine I gave you that, 62% have a king-size bed, 43% have a view of the room, a view of the square, 38% have both. Remember, to fill in the two-way table, you're going to add and subtract until you fill everything in. So if I do 100 minus 43, this is 57, don't have a view. 100 minus 62, 38, don't have a king-size bed. 62 minus 38 comes out to be 24, don't have a view. 57 minus 24 comes out to be 33. Okay, have a no view but have a king-size bed. And then we have 5, have no king-size bed, but have a view. Okay, so it says, does the data in the table suggest that the events a room has a view of the square and a room has a king-size bed are independent? The way you're going to figure this out is you're going to do a conditional probability and set it equal to an individual probability. Whatever the first letter is in your given, before you're given, that's the individual one you're going to check it against. Basically what you're saying is the chance that A occurs the same out of everyone as it is out of the group of B. That's basically what you're saying. So is the chance of having a room with a view the same out of every room as it is out of the room with the king-size beds? So you're going to check a conditional probability, and it doesn't matter which order. So let's say I do P of K given V. The probability I'm going to check that against is the probability of just K by itself. Okay, so the probability of K happening. K is 62 out of 100. Okay, so that's 62 out of 100, or 0.62. K given V. So given V means we're going to focus on the rooms that just have a view. Okay, 43. Okay, so out of those 43, how many have a king-size bed? 38. And now let me check these decimals. 38 out of 43 comes out to be 0.88. Okay, 62 out of 100 is 0.62. The fact that these are not equal, so not equal means they are not independent. It means that the chances of having a room with a view affects the chances of having a room with a king-size bed and vice versa. Now, if you had wanted to, instead of doing P of K given V equals PK, you could also have done P of V given K equals P of V. Okay, and it still comes out to be the same thing. They're not going to come out to be equal, so the fact that they're not equal means that they're not independent. Okay, or they're dependent. That might be the word you're looking for. Take a look at number 2. If the probability of A and B is 0.28, and the probability of A is 0.7, and the probability of B is 0.4, does the information suggest that the events A and B are independent? So what I might do with this is I might set up a two-way table. Since I'm dealing with decimals that have 2 decimal places, I'll make it a hypothetical 100 table. So I would have A and not A, B and not B, and I have my totals adding up to 100. Okay, so the probability of A would be 70 out of 100. 0.7 is really 70. Okay, so 30 would be not A. B would be 0.4 or 40, so 60 would be not B. 28 would be A and B together, so I can just add and subtract. 28 minus 40, oopsies, 40 minus 28 comes out to be 12 for not A, 18 then to add that up to 30, and 60 minus 18 would add up to be 42. Okay, so does the information in the table suggest events A and B are independent? So you can check this conditional probability. Probability of A given B equals the probability of A. Okay, so A given B. So given B means I'm going to focus only on the row B. So out of those 40 that satisfy B, how many also satisfy A? That would be 28. Okay, see how that compares to the probability of A by itself? Technically, you don't even need to calculate that from the table. It is 70 out of 100, but you're given probability of A, so I wouldn't recalculate that, 0.7. 28 out of 40 comes out to be 0.7, so the fact that these are equal, okay, so equal means they are independent. Okay, the probability of A does not affect the probability of B. Now, an alternative way, by the way, just for yourself, if you want to be able to check this, if the probability of A times the probability of B equals the probability of A and B put together, that's another way of showing that these would be independent. So the probability of A is 0.7, the probability of B is 0.4. Does that equal 0.28? Yes, since those come out equal. That's how you definitely know that these are independent. I personally like the table better, but obviously that's just an alternative just in case that makes your life easier. Last example. So it says a class of 40 students has 8 honor students and 17 athletes. 4 of the honor students are also athletes. 1 student is chosen at random. It can be concluded the events a student is an honor student and a student is an athlete are, and this is a multiple choice problem. Well, I'll tell you right now, they're not going to be complements. Complements would be things like the chances of it raining is 0.6, then the chances of it raining would be 0.4. 2 things that add up to be 1. Mutually exclusive means events that can occur at the same time, or events that don't occur at the same time. It tells you right here, you have 4 students that are both honor students and athletes, so it's not going to be that they're mutually exclusive. Most likely one of these questions is just checking to see, are they independent or are they dependent? So this time I'm going to make a two-way table, but because it says we have a class of only 40 students, okay, I'm going to make it so that I have this out of 40. Okay, oops. So it says that my total adds up to be 40. So now it says, in a class of 40 students, we have honor students and not honor students. We have athletes and not athletes. So 8 of our students are honor students. That would mean that 32 are not honor students. 17 of our students are athletes. So if I do 40 minus 17, that means that 23 of them are not athletes. 4 students are both honor students and athletes. So 4 students are both honor students and athletes. Now add and subtract to fill in the values in the table. 4, and then I have 13, and then I have 23 minus 4 is 19. Okay? So now the question is, honor student and athlete, are they independent? So you're either going to check P, honors given athlete equals honors, or check athlete given honors equals athlete. Okay, you choose either one of those is going to give you the correct answer. I'll just do the one on the left because that's the first one I wrote. So the probability of honors given athlete. So given athlete means I'm going to focus on just the athletes. So of the 17 kids in that group, how many of them are honor students? 4. Okay. What's the chances of having an honor student? Chances of having an honor student is 8 out of 40. Okay, so out of all the students, only 8 of them are honors. Let's check those decimals. 4 divided by 17 is 0.235. 8 out of 40 comes out to be 0.2. I know they're close to each other, but they are not exactly the same. So the fact that they're not equal means they are not independent, which means that being an honor student affects being an athlete and vice versa, or the chances of picking an honor student is affecting the chances of picking an athlete. So the answer is that 2, they are dependent.